Have you ever wondered why time only seems to move forward? I mean, why do we remember yesterday but not tomorrow? Well, the answer isn't in some futuristic clock or a complex calendar. It's actually hidden in one of the most fundamental, rock-solid laws of the entire universe. And it explains all sorts of things we see every single day.
Yeah, think about it. You see this stuff constantly. Ice cubes melt in your drink, a nail you leave outside gets rusty, and a ball will always roll downhill. We call these processes spontaneous. They just happen. But have you ever seen a puddle of water on a warm day suddenly decide to freeze itself back into a perfect ice cube? Or a rusty old car magically turn shiny and new again? Of course not. It just doesn't happen. So what is going on here? What's the deep physical reason for this one-way street we call reality?
This one-way nature of, well, everything presents us with a really fascinating puzzle. And to solve it, we've got to figure out what really makes a process kick off all by itself.
Okay, so our first guess is pretty intuitive. And honestly, it makes a lot of sense. That ball rolling downhill? Perfect example. It's just moving from a state of high potential energy up at the top to a much more stable, lower energy state at the bottom. In chemistry, we call a process that releases energy exothermic, and we measure this change as something called enthalpy, or just delta H. For a long time, scientists thought this was the whole story. If a reaction releases energy, if its delta H is negative, it's got to be spontaneous. Simple, right?
Well, this is where that nice, simple theory completely falls apart. Think about those instant cold packs you use for an injury. You know, the ones you snap the little thing inside, give it a shake, and it gets cold. Like really cold. That feeling is the pack literally sucking energy or heat away from your skin. It's an endothermic process. Delta H is positive. It's taking in energy. Yet, it happens spontaneously the second you mix those chemicals. So, if it's not just about releasing energy, there has to be something else. Another, maybe even more powerful force at play.
So, what is it? What's this missing piece of our puzzle? The hidden variable that explains why a cold pack gets cold all on its own and why ice melts in the first place? Well, it has a name. Entropy.
Now, hold on. You've probably heard entropy described as just disorder or randomness. And that's kind of right, but it's a bit sloppy. A much better way, a more accurate way, to think about it is as a measure of dispersal. Entropy literally measures how spread out the energy of a system is. The more spread out and dispersed that energy is, the higher the entropy. And it turns out, the universe just loves this dispersal. This image here is a fantastic way to picture it. Imagine you've got a few gas particles in this container. What are the odds that they'll all just happen to be crammed into one tiny corner? Pretty low, right? But what are the odds they'll be more or less evenly spread out through the whole space? Much, much higher. It's not because of some weird force pushing them apart. It's just pure statistics. There are simply way more ways for things to be spread out than for them to be clumped together. And that most probable state, the most spread out state, is the state of highest entropy.
And we can see this exact principle in the real-world numbers. Just look at the values for water. So liquid water has a standard entropy value of about 70, but water vapor, steam, a gas, has an entropy of almost 189. Why that huge jump? Well, it's because in a gas, those water molecules are zipping all over the place, totally free. Their energy is way more dispersed than in a liquid, where they're all kind of stuck together. More dispersal means higher entropy. It's that simple.
All right, so now we have two big ideas competing with each other. We've got enthalpy, which is the tendency to release energy, and we have entropy, the tendency for energy to spread out. So which one wins, and how do they work together? Well, to answer that, we have to zoom out and look at the bigger picture.
In thermodynamics, we like to divide the entire universe into two parts. It sounds dramatic, but it's simple. There's the system, that's the reaction or thing we're actually looking at, and then there are the surroundings, which is literally everything else in the universe. So when our system releases energy, like you see on the left, that energy doesn't just disappear. It has to go somewhere, right? It goes out into the surroundings. And when our system absorbs energy, on the right, it's got to take it from the surroundings. This exchange is everything.
And here it is. This is the big one, the second law of thermodynamics. This is one of the most fundamental, most unbreakable rules in all of science. It says that for any spontaneous process, anything that happens on its own, the total entropy of the universe, that's the system plus the surroundings, must increase. A reaction can actually decrease its own entropy, sure, but only if it causes an even bigger increase in the entropy of its surroundings. The universe as a whole always gets more dispersed.
Now that's a mind-blowing insight for sure, but it also creates a massive practical problem.
I mean, if we want to predict whether a chemical reaction is going to happen, do we really have to measure the change in entropy for the entire universe? That seems, well, impossible.
So that's the million-dollar question, isn't it? How can we use this amazing universal law in a way that's actually useful? How can we know if something's going to happen just by looking at the system itself, without having to worry about, the rest of the cosmos?
The answer comes from a truly brilliant piece of scientific genius from an American scientist named Josiah Willard Gibbs. He came up with this equation for something he called free energy, which we represent with a G. And this beautiful, elegant little equation, G equals H minus Ts, it combines the enthalpy, H, and the entropy, S, of just our system, along with the temperature T, into a single powerful value that does all the heavy lifting for us.
And here's the punchline. This is the magic of it all. If the change in that Gibbs free energy, what we call delta G, turns out to be a negative number, the process is spontaneous. That's it, period. We don't have to measure the universe anymore. We just have to calculate this one number for our system, and it tells us with certainty whether or not something is going to happen all by itself. It's an absolutely incredible predictive tool.
Now, if we look back at that Gibbs equation, there's a crucial variable we kind of glanced over: temperature. The T in that formula isn't just a background detail. A lot of the time, it's the actual deciding factor.
This table breaks down all the possibilities. So look, if a reaction both releases heat and increases entropy, it's a win-win. It's going to be spontaneous at all temperatures. Delta G will always be negative. If it absorbs heat and decreases entropy, nope, never spontaneous. But the really interesting cases are the other two. Think about water freezing. It actually releases heat, but it decreases in entropy because it's getting more ordered. This only happens spontaneously at low temperatures. And the reverse, ice melting, absorbs heat but increases in entropy, so it's only spontaneous at high temperatures.
And this graph just visualizes that trade-off perfectly. You can see right here how for some reactions, the line for delta G starts off positive, meaning non-spontaneous. But as the temperature goes up along the bottom axis, that line eventually crosses zero and becomes negative. And that crossing point, that is the exact temperature, like 0 degrees Celsius for ice, where a process flips from being non-spontaneous to spontaneous. It's all about that balance. So we've solved our puzzle. We know what drives things to happen. But that rule, the second law of thermodynamics, it leaves us with one last, really deep thought. If the entropy of the universe is always, constantly, and irreversibly increasing, then that increase gives time its direction. The past is, by definition, the state of lower entropy, and the future is the state of higher entropy. The reason a broken egg never unscrambles itself is the very same reason we can't remember the future. It's the arrow of time, defined not by clocks or calendars, but by the relentless, unstoppable march of entropy.